Good morning. Here we can see the one example for geometric representation of signal. So in previous session already we have seen how to represent geometrically a signal. So if we are taking any set of m energy signals Si of t as a linear combination of n orthogonal basis functions where n's value will be less than equal to m. So here we are taking for each energy signal's time as a t seconds. So we will get energy signal Si of t that is equal to summation I equal to 1 to n Si of j, that is the we are saying as a coefficient, scalar coefficients, and phi j of t that is the orthogonal basis functions. So you will get Si of t that is equal to summation I equal to 1 to n Sij phi j of t. So here we are taking time is equal to in between 0 to t seconds, and I equal to 1 to up to m. So here you will get the coefficient, scalar coefficient as Si of j that is equal to integration 0 to t Si of t phi j of t dt, and we will get the real valued basis functions that is phi j of t. So you will get integration 0 to t phi of t phi j of t dt equal to 1 if I equal to j, and that will be real valued basis function equal to 0 if I is not equal to j. So we can say the set of coefficients can be viewed as n dimensional vector we can denote by Si, and if we are bearing one to one relationship with transmitted signal Si of t. So here we have seen the synthesizer and the analyzer for the set of signal vectors. When we are talking about the synthesizer, we are supposed to take the signal as Si of t, and when we will talk about the generating signal at the analyzer, we can say that as a Sj of t. So we have seen that here we are taking the signal Si of t. So we can say each signal in set Si of t is completely determined by vector of its coefficients. So we can take as Si equal to, in matrix you can write in column from Si1 Si2 up to Sin, where we are taking I value is from 1 to up to m. So here we are saying the signal vector Si can be extended to 2D, 3D up to n dimensional Euclide's space geometry. So it will provide us mathematical basis for geometric representation of the energy signals. So we can use that mathematical analysis in the noise analysis. So here we are supposed to see now about length of vectors, angles between vectors, and square value. We will see these things. So here we can say you will get the Si modulus square, double modulus square equal to Si transpose matrix into Si. So here you can say you will get summation I equal to 1 to n Sij square. So now we can see here the waveform, the diagram for how we are representing geometric representation of a signal in 2-dimensional. So we can see one example illustrating the geometric representation of signal for the case when n equal to 2 and m equal to 3. So you can observe here the waveform. So here we are supposed to see what is the relation between the vector representation of a signal and the energy value. So here when we are saying the definition of average energy in signal, what we are taking energy signal? We are taking E equal to integration 0 to t Si square dt. Si square t dt. So here we are saying Ei is nothing but the energy value. Si of t is the signal which we are transmitting. So we can say you will get Si of t as S of t equal to summation I j equal to 1 to n. When we have seen energy valued signals we are taking for time t, you will get that in the form of scalar coefficient and the basis functions. So we are taking that Si of t or Sij of t, we are taking Si of t that equal to summations j equal to 1 to n Sij phi of t dt, or instead we can take here, we can take that, or we can take where we will get here Sij equal to, here we are writing Si of t equal to summation j equal to 1 to n Sij phi j of t, where we can say Sij will be equal to integration 0 to t Si of t phi j of t dt. So here we can say Si of t is nothing but the signal we are transmitting. So we can say Sij as a scalar coefficient and phi j we can say as a basis functions. So we can say here the real valued basis functions phi j of t are orthogonal to each other. So we will get, we have seen that we will get 0 to t integration phi I of t into phi j of t dt equal to 1 if we are taking I equal to j, and we will equal to 0 when we are taking I is not equal to 0, I is not equal to j. We have seen this concept, I am just showing you. You can see here we are taking, you will get the real valued functions when we are taking when we are representing geometric representation of a signal. At that time we are taking energy signal equal to scalar coefficient into a orthogonal basis functions. So here so here we can say you will get here energy functions equal to integration 0 to t Si square tt dt. But we can say Si of t is nothing but equal to summation j equal to 1 to n Sij phi j of t. So when we are putting that value in our first equation, that is the energy signal Ei equal to, we can put Si of t value in the equation 5, 10. So if we are putting, you will get after substitution. If we are regrouping that, you can remoderate our equations like 5.11. So here we can say phi j of t, that is nothing but real valued basis functions. The basis functions, basis coefficient functions is orthogonal. So we will get Ei equal to double modulus Si square. So here we will get, that is nothing but summation j equal to 1 to n Sij square. So here we can take the formulas for two signal instead of one signal if we are taking the pair of signal. So we can assume we have pair of signal Si of t and Sj of t. So our equation will become, if we are representing this signal by a vector, you will get Si of j, that is equal to integration 0 to t Si of t into Sk of t dt. So we can take Si of transpose matrix into Sk. So here we can say inner product of signal is equal to inner product of their vector representation. And we can say inner product is invariant to the selection of the basis functions. So here we can see about now the Euclidean distance between these two signals. Here we are taking S I of t and Sj of t. The two, it means what? The pair of signal. So we can say the Euclidean distance between 2 points we can represent by the vector that is equal to, you will get as double modulus Si minus Sk, and the squared value is given by double modulus Si minus Sk square equal to summation j equal to 1 to n Sij minus Skj square. So we can take that as integration 0 to t Si of t minus Sk of t square dt. So here now we can see, because we are supposed to see some parameters for this signal. You can see here, when we are studying about the generating representation of signal, we will require the length of vector. It is nothing but the distance, absolute value, the angle between vectors, and squared value, that is the Si square. So here we have seen now just about the distance. Now we will see about the angle. So here we have seen, you will get the Euclidean distance between 2 points which we are representing by the vectors. We will get equal to Si minus Sk. So we can take that squared value of the Euclidean distance, that is the double modulus Si minus Sk square equal to integration 0 to t Si of t minus Sk of t square dt. Now we are supposed to see about the angle between these two signals, Si of t and Sj of t. So here we can say the cosine of the angle theta ik is in between the two signals. Which signals? Si and Sk. That is equal to the inner product of these two vectors. Here we are taking the two signals Si of t and Sk of t. So we can say the cosine of angle theta ik between two signals Si and Sk is equal to the inner product of these two vectors, which will divide by the product of their norms. So here you can take the product of norms in the denominator and the inner product of these two vectors in the numerator. So you will get cosine of that angle. So cos of theta ik equal to Si of t transpose matrix of Si into Sk upon double modulus, or we can say a norms, double modulus Si, double modulus Sk. So we can say the two signal vectors are orthogonal if their product, if their inner product is nothing but which we are taking in the numerator. So we can say if their inner product Si of t Sk is 0. So you will get here cos theta k ik equal to 0. This is the angle between two signals. Now we are supposed to see squads in equality. We will see that. So here we can define squads in equality as we can explain that mathematically as integration infinite to infinite minus infinite to infinite S1 of t S2 of t dt square equal to integration infinite to infinite S1 square t dt into integration minus infinite to infinite S2 square dt. So we are accepting this proof without any proof for that. Now we are supposed to study about the gram schemed organization procedure. So here also we are supposed to represent geometrically a signal. So here now we are assuming the principle of Gram-Schmidt orthogonalization, in which we are supposed to assume a set of m energy signals, that is the Si of t, where we are taking I equal to less than equal to m. It means what? 1, 2 up to m. So here when we are assuming a set of m energy signal, we can denote the signal as S1 of t, S2 of t up to Sm of t. So we can express that as linear combinations of n orthogonal basis functions. So orthogonal basis functions we are taking as a phi ij of t. So here we can say we can express set of m energy signals S1 of t, S2 of t up to Sn of t as a linear combination of n orthogonal functions. So you will get Si of t equal to summation j equal to 1 to n Sij phi j of t. So here we can say when we are supposed to study about the gram-Schmidt organization, at that time we are supposed to follow some steps. So here when we are taking the set of m energy signals, we can define that as the first basis function starting with S1. So here we are taking phi 1 of t, because here we are defining first basis functions, and first basis function we are denoting by basis function phi. So first basis phi 1 of t. So we can define the first basis function starting with S1, as here we will taking the energy signal as even. So you will get phi 1 of t equal to S1 of t upon square root of E1. After that we are supposed to express our S1 of t, the first signal. We are supposed to express that using the basis functions and energy related coefficient S11. So you will get S1 of t equal to square root of E1 into phi 1 of t. But here we are taking expressing S1 of t as a basis function and energy related coefficient S11. So phi 1t remains as it is, but instead of square root of E, energy of signal, we are supposed to write as a energy related coefficient S11. So square root of E1 को तुम क्या लिख सकते हो? S11. Now latter using S2 define the coefficient S21. Similarly, the same step 2 we are supposed to do to define S21. So we can define the coefficient S21 equal to, you will get as integration 0 to t S2t phi 1 of t dt. So here when we are representing that signal, that is nothing but the second signal, the second energy signal coefficient S21. After that we introduce intermediate functions. We can call intermediate functions, we are denoting by G2 of t. So you will get G2 of t equal to S2 of t minus S21 phi 1 of t. These are the some steps which we will require for Gram-Schmidt orthogonalization. So when we are introducing the intermediate functions G2 of t equal to S2 of t minus S21 phi 1 of t. So here you will get orthogonal to the orthogonal basis functions. So we can now define the second basis functions, that is the phi 2 of t. So here you will get phi 2 of t equal to intermediate functions G2 of t upon square root of integration 0 to t G2 square t dt. After that we will substitute G2 of t using S1 of t and S2 of t. So now our equations for the second basis function will become phi 2 of t equal to S2 of t minus S21 phi 1 of t, because here we are substituting, instead of intermediate functions we are supposed to substitute this value as S1 of t and S2 of t. So you will get like that. So like equation 5.24. So you will get phi 2 of 2 equal to S2 of t minus S21 phi 1 of t upon square root of E2 minus S21 square. So here you can say phi 1 of t and phi 2 of t are orthogonal. So you will get 0 to 2 phi 2 square t dt equal to 1 and 0 to t phi 1 t into phi 2 t equal to 0. So here we can say about the Gram-Schmidt organization. Now, in next class, we will see for n-dimensional space. Here only we have seen for two-dimensional space. Here we are taking the m energy signal. We are supposed to see the procedure, some steps, how we are taking the Gram-Schmidt organizations. Remaining we will see in the next class. Thank you.